This is going to be a recording of the last portion of Chapter 19 on conjugate additions to alpha-beta unsaturated aldehydes and ketones. And before we can talk about conjugate addition, we need to make sure we understand what portion of the molecule we're talking about and to look at some examples. So we talked about the fact that in some of the older style of nomenclature for aldehydes and ketones and other carbonyl compounds, that they use Greek letters to denote positions relative to the carbonyl. And so that's where we're going to see this alpha and beta be used. So in this first example, this cyclohexenone, the double bond is between the position which is one carbon away from the double bond and the next carbon after that. And the Greek lettering system would put those as alpha and beta. Now you notice that this now makes this molecule unsymmetrical, and so I have a different alpha and beta over here. And of course, in the original cyclohexanone, it wouldn't have mattered which side you put the double bond on. So you'll see the same thing in this molecule. Once we have the double bond in here, there's a difference between this alpha and beta position relative to this one, but originally there was no difference. An aldehyde only has an alpha carbon on one side, and so this alpha-beta unsaturated aldehyde, there's only one side that's alpha, that's labeled alpha and beta and so forth. So there's examples of both types of alpha-beta unsaturated aldehydes and ketones. So the reason that this is an important position in the molecule is related to the fact that this system is conjugated. And you remember in chapter 14 we talked about the fact that in a conjugated system that all of the electrons in the extended pi cloud belong to the whole molecule, and there's not really an isolated double bond, and the same thing is true here. So even though we draw this picture like this is a double bond and this is another double bond, this whole system is a unit. And we can kind of look at that by thinking about the polarity of this bond. The carbonyl has positive character on the carbon and negative character on the oxygen. And I've shown you before in the extreme case, you kind of separate that charge and put a plus charge here. And you'll notice that that's actually allylic, and that was other terminology that we used. One carbon away from this double bond is the allylic position. So we can draw a further resonance structure for that, where we share the positive charge down here at this other carbon. And so if you kind of draw a summary of what's going on here, both the carbonyl carbon and the beta carbon have positive character because of the positive charge being shared at these two positions in this resonance structure in the middle. And so what that means is that there are certain groups that will preferentially react with the beta position carbon instead of going to the carbonyl carbon, perhaps for to stay away from a negative group, to stay away from this negative group. And really you're just going to have to memorize which groups they are that specifically will react down here at the beta position. And in this book there are only going to be a couple of examples, but really there are other examples. It's just they've only chosen to show you a couple of those. So what's going to happen is that the conjugate addition is we're going to see a group add to this beta position carbon, and one of the things that will do that specifically is amines. And we already looked at amines reacting with the carbonyl carbon, and remember the products were either amines or enamines. And in the case, and it mattered which degree of amine you had as to which one of those two things would happen. In the case of these alpha-beta unsaturated molecules, you get the same type of product regardless of whether you use a primary or a secondary amine, and it's preferentially going to go to that beta position. And then we're going to look at lithium dioxyribonucleates, which do not react with plain old saturated ketones or aldehydes, and in fact we use lithium dioxyribonucleates to be able to make ketones from acyl halides. And at that time I mentioned the fact that there would be some limitations that we would have to use that to make saturated ketones, and now you can see why. And as I said, there are other examples, but these are the only ones we're going to use in this book. And what really happens is that through the process of the conjugate addition, it looks like 1,4 addition. If you go back to chapter 14 where we talked about 1,4 versus 1,2 addition, these conjugate additions look like 1,4 addition, and they end up at an enol stage. We haven't talked a lot about enols, but remember those are also called vinyl alcohols. And then they rearrange back to a carbonyl through an equilibrium that favors the carbonyl form. And it kind of looks like all you did was react the alkene portion of the molecule, but in reality, an isolated alkene wouldn't have done any of this. So we'll have to look at some pictures to fully appreciate this. And again, we're going to start with amines, and you can't really tell the difference in the products like you could with plain aldehydes and ketones. In these alpha beta unsaturated ones, you get the same type of result from either primary or secondary amines. So here's an example of an amine, and I forgot to put the pH requirement in here. But so at the beta position, this is where this nitrogen's unshared pair of electrons is going to react down here with a positive character at the beta position, and the electrons are going to flow through to the oxygen, which is where they were anywhere. And then this hydrogen technically kind of moves over to here, or you could look at the electrons flowing back and picking up the hydrogen here. In any event, if it had picked up here, it would be an enol, and that's an equilibrium with a keto form. And so when we get the hydrogen over to here, then, as I said, it looks like all that happened was that you changed this alkene, that you added the hydrogen to one end and the nitrogen to the other end. But in fact, if it hadn't been this alpha beta unsaturated ketone, it wouldn't have reacted at all. And we only needed one bond here, so that's why secondary and primary amines both work, because we only need to make one new bond to that nitrogen, and we just take the place of one hydrogen. The other thing that does conjugate addition to alpha beta unsaturated ketones and aldehydes are the lithium diorganocuprates, and so here's an example, a couple of examples for that. And you'll notice that we have an aqueous acid in here to sort of finish this up, and it again is because it goes through the conjugate addition where it puts the hydrogen at this end, double bond here, and the carbon down here, and then it's in equilibrium with the keto form again. So ultimately what it looks like you did was you just put a hydrogen and the carbon onto the either end of this double bond, but in fact it wouldn't, these guys don't react with plain ketones like this. And this reaction partners really well with something we're going to see in a couple of later chapters from now, and where we can put carbon onto this beta position, or we could put carbon onto the alpha position, and so being able to pick and choose is really nice. And in this example, I picked a little bit more complicated lithium diorganocuprate, so you notice there's a double bond in here. And so this carbon right here attaches to this beta position carbon. And so if you look, these three carbons right here are the ones that came in here in the lithium diorganocuprate, and then these three in this portion of the molecule are these three. And so we lose the double bond, and we get that new group at the beta, on the beta carbon. So those are examples of the conjugate addition, and like I said, we'll kind of revisit this and also the Cannizzaro reaction in chapter 22 and 23. So the Cannizzaro was covered in the biological addition section of this chapter, and so that and the conjugate additions all have some biological significance. And what you need to do in this chapter is you do need to be able to name and recognize aldehydes and ketones. Common names are important, as well as IUPAC. And make sure you understand these alpha beta position designations, and you can find things in the molecule where we're talking about when you use that terminology. And go back and review and make sure you understand where we are in the redox scheme. It's very important that you keep track of the fact that the carbonyl in aldehydes and ketones is at a different redox level and behaves differently, does different reactions than the carbonyls in carboxylic acids and their derivatives. And we've had a few reactions in this chapter that are you're going to see completely different kinds of things um, in the carboxylic acid and derivatives chapters. So you need to review how to make aldehydes and ketones, and also look at a couple of new things that were in this chapter. And then, of course, most importantly, we did a lot of reactions with nucleophiles. And I put them in the order hydrogen, oxygen, carbon, and then nitrogen nucleophiles. And that's not the order that they went in the book, but we actually did cover all of the sections that were in this chapter, just in a different order. So make sure you know how to find the nucleophilic atoms, and look at the patterns. The nucleophilic addition reactions typically add the nucleophile and a hydrogen across the double bond of the carbonyl, and then a few of them can go further. Acetal formation was a further step, and then things like the amines and Wittig reactions ended up with a double bond to the nucleophile. But they all start out the same way, and so that repetitive pattern may help you to kind of get your studying organized in that way. And the mechanism that's most important in this chapter is the mechanism of acetal formation. It's important biologically. I've mentioned that before. And we're going to talk about carbohydrates, and that's really where it comes into play especially. And so that's the one that you need to know. And that's the end of this chapter.